Hello, and welcome to this video where we're going to be talking about calculus topics in special relativity. Specifically, we're really going to be focusing on how calculus leads to an expression of the second law of Newtonian mechanics, so Newton's second law, but in a relativistic form. All right, and I have discussed this in a previous video, and you can look here at the final result that this is special relativity's application on, well, this Newton's force, and we got there through using the mathematics of calculus. Okay, so we have a very different version of the second, the second law of Newton that what normally tells us F equals ma, but now with relativity, we're going to be looking at two different components of that acceleration. A component of acceleration that's parallel to the force and a component of acceleration that's perpendicular to the force. Because of the nature of special relativity, and since it only affects anything in terms of length contraction and time dilation, it only affects space that is parallel to the direction of motion. That means that we have an asymmetric effect between what's happening in the direction of motion and everything that's not in the direction of motion. So when we have this idea that the force is pointing a certain way, now the acceleration is not. So this creates a big difference in physics from classical physics to relativistic physics, where acceleration is no longer parallel to force. Not always, okay? And never exactly once we get up to relativistic speeds, which is something we certainly took for granted in classical mechanics, that A is always parallel to F net, at least, right? Not an individual force, but the net force. Not the case here, okay? So as I said, we were able to show this by just following through some natural steps. Okay, now we're really gonna put it to use. So the first of the two examples that we're going to go over is one involving a certain small mass. Okay, so we're told that we have a mass of 1.89 times 10 to the negative 9 kilograms. Okay, and we're told that we're going to bring this mass up to a final speed, which is 95% the speed of light, so 0.95 c. Okay, in part A, we're actually not going to be doing anything that is using this new relativistic second law. Instead, in part A, we're really just going to take a look at how much work it took to get to this point. So that means that since we had a particle that started at rest, and we're going to bring it up to that final speed, all right, then we're going to, so this is for the rest of the motion, not for rest, right? But the work that was done by gravity would have to be equal to the change in kinetic energy, okay? Well, here we know that the kinetic energy that is reached at such a high speed is relativistic kinetic energy. So now we have that the work done by gravity, I'm going to use big G for gravity because this isn't gravity on Earth, but this gravity somewhere, all right, is then going to be equal to K relativistic. All right, so then we can go ahead and, we can solve for gamma. That's always a great idea. And then that would tell us, how much work it took. Okay, so let's go ahead and take a look at that. So gamma for 0.95 c, all right? So, and oh, by the way, K relativistic just has the form that it is gamma minus 1, not deriving it here, times mc squared. The actual velocity shows up in the gamma expression, and let's go ahead and find out what that is. All right, so if we're going to go ahead and find the gamma value, which is known as the Lorentz transformation, all right, then it is 1 minus v squared over c squared. In this case, it's just going to be 1 minus 0.95 squared, right? Because it's just the c part cancels out. So 1 minus 0.95 squared. Okay, so let's go ahead and get the value for that. All right, so they'll call this our G value for our gamma expression. All right, and it's just going to be 1 divided by the square root of 1 minus 0.95 squared. Okay, so that gives us a gamma value of 3.21. The bigger the value of gamma, the bigger the effect of relativity. This is significant, but not huge. That's 3.20, excuse me, my rounding was off. Okay, and gamma does not have units, okay? It's a dimensionless quantity. All right, so with that out of the way, let's go ahead and find the work, okay? So then the work that was done is, the work done by gravity is simply going to be equal to that expression, gamma minus 1 times mc squared. So with the numbers, it will be 3.2 minus 1 times the mass that we are given. So the mass, of course, matters here, 1.89 times 10 to the negative 9, and then multiplied by the speed of light squared. All right. So let's go ahead and see what we get. This is going to be in joules. All right, so we'll have, this will be our K value, which is also our work, but I'm just going to go ahead and call it our K value because it's our relativistic kinetic energy. And it's just going to be G minus 1, of course, in parentheses, and then that's just going to be times. Let's go ahead and drop our M value in here that's specific to this particle. All right, so M is just going to equal 1.89 times 10 to the negative 9. Okay, not quite. There we go. And then, of course, we wanted to find C. Okay, so then C will just equal 3 times 10 to the 8. All right. Okay, that all checks out. So up here then, I'll just be able to drop in the MC squared. Okay, so M and then times C squared. Okay, so failed to put an M in there. There we have it. Okay, so our energy in, it's not that small, I guess. 3.2, yeah, I mean, I guess, because I guess it's fairly massive. We're not, talking about the kinetic energy of an electron or something. It's a fairly massive particle, many orders of magnitude larger. So let's see then. We have a significant amount of joules here. What if we go ahead and divide that? We'll just create another, let's go ahead and enter down here. If we just take K and divide it by 1,000, what if we divide it by 1,000,000? So we put it in that order of magnitude. So it's 374 million, okay? So we'll go ahead and write it like that. So 3.74, I'll go ahead and do this, times 10 to the 8, and then that's going to be joules. All right, looks good. All right, so that out of the way, we can go on to part B, all right, which is going to be the new stuff. Okay, that was definitely just review, something I wanted to squeeze in there. All right, just an interesting topic. But moving on to part B, if the net force, I see I have two part B's, this should be C over here. But anyway, so if the net force is parallel to the particle's velocity of 0.95 c, what is the particle's instantaneous momentum and acceleration? Okay? So in this case, we have the net force is parallel to the particle's velocity of 0.95 c. Okay? So that means there's going to be no component that's going to affect things, right? There is no component that is perpendicular. So we're only going to have the parallel effect, okay? So if we consider that, right? So in the case where things are parallel, what do we have, right? Well, we've got an acceleration, right? So basically there's always two forms of acceleration. So relativistic acceleration, we'll write it like this. It's kind of because there's different ways of coming at this. I think this is a helpful way of thinking about it. So now that we know that relativistic acceleration is fundamentally not necessarily equal to the direction of the force, except in this one case where the force is parallel to the velocity, but in any other case where the force is not parallel to the instantaneous velocity, so instantaneous force not parallel to instantaneous velocity, they can be changing as functions of time or distance, but at some moment in time, some snapshot in time, if they're not parallel, then the acceleration will not be parallel to the force. That assumption from classical mechanics, okay? That's the idea. So in any case, at least subtly, they will not be parallel. So that means that relativistic acceleration as a vector has two components that are relevant to think about. The parallel component, as in parallel to the velocity, and the perpendicular component, okay, as in perpendicular to the velocity. Okay, so yep, and that's because it's just to the direction of motion. All right, and in this case, we only have a parallel one because you only get a force when we have, or rather you only get an acceleration when you have a force. So for part B, what I mean by that is that the relativistic acceleration will just be a parallel. Actually, I was going to replace that with force to show you. This would just be F parallel, all right, as a vector, and then divided by the coefficient gamma cubed m, all right? And then the perpendicular component would be just divided by gamma m, right? But we know that there is not a perpendicular component to force because all the force is parallel. So, we could write out the whole expression and then just send one of them right to 0. Right? We don't need that one. So it's a much simpler case. We don't have to worry about too much. It's meant to be a kind of proof of concept introduction, okay? Now, obviously there's already an interesting effect of relativity in terms of just the sheer numerical relationship between acceleration and, in this case, parallel force. But I would say that relationship is nowhere as interesting as the fact that the vectors aren't parallel, all right? But no matter, we'll go ahead and find the number here. All right, so perpendicular, yep. So instantaneous momentum and acceleration. So first we'll find the acceleration because we're already working on it. So then the acceleration is just going to be equal to the parallel, all right, in magnitude, all right, and then we'll go ahead and it's just whatever direction it's heading in. So we've already cleared up. It's all one directional, 1D here, and so then we simply put the force value that we're given because we're told that this force value just remains constant, and it's 1.42 after 10 or times 10 to the negative 6. Okay, this is once our particle finally reaches its cruising velocity of 95% the speed of light, all right? Now, that's not fair, actually, because it's actually still speeding up. But we don't care, right? We just care that there's a force. I say it's still speeding up because it's obviously still force acting on it, all right? And you might stop and think, is this all an inertial reference frame? No, obviously we're talking about accelerations here, the very definition of non-inertial reference frames. So you might think that this isn't special relativity. Is this general relativity? No, this is just applying special relativity to particular instances and using it to find instantaneous values. Kind of like we use conservation of energy to find instantaneous values in systems where we cannot solve for displacement over time. Likewise, we do not have the tools using special relativity to solve for displacement over time in terms of forces at relativistic speeds, but we can look at little snapshots in time, okay? So we don't know exactly what will happen next, other than trying to extrapolate one small step at a time, but we can still get these values accurately. So with that in mind, there is still a force, so there's still some sort of acceleration. We don't care what the final velocity is, we just care what the original velocity is, right? Because eventually it'll be going faster or slower. But then we divide by our gamma cubed m value. We know that gamma is 3.2 because that's the same number, okay? And that will be cubed, and then we'll put the mass in there. So 1.89 times 10 to the negative 9 kilograms, okay? So with all that together, we are ready to actually solve for the value of acceleration, which is the net acceleration in this case. All right, so we're just going to go ahead and call this A1, okay? This is the first acceleration value that we have been asked to calculate. And we also want our F value because we'll probably use that more than once. Certainly, in fact, okay? So here we'll drop in our 1.42 times 10 to the negative 6. Surprised I didn't already define that, all right? No, it hasn't come up, that's why. Okay, all right. So then back to this one, we're actually going to have F. We'll divide by gamma cubed and everything. So let's drop our F in the numerator. All right, down here we'll put our g cubed term because that's representing our gamma. And then it looks like we're just going to multiply by m. Okay, so there we have it. And we end up with 22.9 meters per second squared. Okay, excellent. So that's one of our values from part B. The only other thing that we were asked for was actually the instantaneous value of momentum. Well, it turns out, thing about momentum, I asked for it, but it never changes. Because momentum doesn't work like this. Momentum is just mass, it's mass times velocity. It's not dependent on this, there's no effect here. There's no acceleration, there's no derivative of velocity. So momentum stays parallel to velocity. So we don't have to worry about some effect because the effect came from the derivative. This whole idea that acceleration kind of decoupled from force, but not so with momentum. Momentum, relativistically, is just going to stay parallel to velocity. So it's just going to be gamma mv, okay? So we can just plug all those in, get our number, all right? So it's going to be our 3.2, all right, for gamma, all right, we'll multiply by the mass, okay, and then finally we'll multiply by the velocity, which is just 0.95 times 3 times 10 to the 8 meters per second, because after all, that is the velocity. All right, so let's see what we get then for our value of momentum. So that will be P, relativistic momentum, but we just call it P. Remember, it's relativistic, and it's just G times M, and then we'll just multiply that times 0.95, and then C. All right, so 1.72 Newton seconds, okay, which would be 7.3, which would be a bigger value than we would have got without relativity. In fact, without relativity, we got precisely, or not precisely, but about 1/3 less, right? Because we just divide by 3.2. Okay, so that's it for part B, all right? On part C, which I will correct over here, let's zoom in a tad, because it's mislabeled as B, but it should be C. All right, so here we have part C. Okay, excellent. So if the net force is perpendicular this time to the particle's velocity of 0.85, what is the particle's instantaneous? Okay. All right, so I guess I changed the velocity here. I might have actually not originally intended to do that, but we'll go ahead and just find a new value. All right, 0.95. Actually, I don't want to have to calculate gamma over and over again, so let's just go ahead and use the same velocity throughout the problem, just for the sake of brevity. All right. In each case, if I was to change the velocity each time, it wouldn't change anything about the problem other than I would just use a different gamma. Okay. We're going to stick at 0.95. Okay. So, all right, just drop that all in as 0.95c. That means we're still changing things because we are changing the angle, but I don't need to change the speed on top of that because would be just feel a little tedious at this time. Not bad practice, but not something I just necessarily want to work on. Okay. So we'll stick it at 0.95c. So, but we get in part C. The whole idea is it's perpendicular this time. That is, again, going to be a somewhat easy case, kind of proof of concept, because now our acceleration is just going to be the perpendicular part, which we again showed with calculus, and that just ends up being just the gamma m in the denominator. So I had it over here. If you look right here, this term went to 0 last time. The perpendicular term, when the entire force is perpendicular, now this term is going to go to 0 and we'll only have this one. Okay, so it's just going to be F perpendicular, all right, over gamma m. Okay, so then that our force is entirely perpendicular, so it'll just be 1.42 times 10 to the negative 6 newtons, and then times 3.2, not squaring it or cubing it or anything this time, all right, times 10 to the negative 9 kilograms. Okay, looks great. All right, so let's go ahead and calculate that one. Okay, that's just A2 if we're being consistent with, or if I'm being consistent with my notation. Okay, and that one will be pretty similar. The only difference is I'm going to have just GM, all right? So otherwise, you can see I can use practically the same formula. Actually, let's just do that. We'll duplicate this one, all right? We'll call it A2, as I spoke about. All right, so let's go do that one. I need a subscript. I think it like unsubscripted. There we go. All right, and then the only difference is I just want to get rid of the cube. Okay. Oh, it still has a spot there. There we go. So 234 now. All right. So notice, right, that not cubing gamma, not having a bigger number in the denominator had a big effect. So the perpendicular acceleration is inherently like going to be larger, and the faster you go, the bigger gamma gets, the bigger discrepancy between the two. And so what's going to happen is that parallel component is just going to get more and more affected until there's almost only, you approach only having a perpendicular component. All right, so 374 or 75 meters per second squared. All right, so as you get faster and faster and get closer and closer to C, you're going to get closer and closer to a point, as I said, where the acceleration is entirely perpendicular to the force. So like, so if you apply a force that is going to be, kind of slightly angled off, you're going to get it to be 90 degrees, right? Now, obviously, that doesn't work if you line up the force exactly with the velocity, because then there's nothing to grow in terms of the perpendicular component. But as long as you have at least 1 degree off of parallel, then that whatever is that perpendicular component is going to end up much larger than the parallel component. Okay, and here's a case where we're certainly more than 1 degree off. We're 45 degrees off. So in this case, finally, the final part, the most interesting part, if the net force is acting at an angle of 45 degrees to the particle's velocity, what is the particle's instantaneous momentum and direction and magnitude of acceleration? All right, and then give the angle of A relative to F net. All right, pretty cool. By the way, P is not going to change in any of these, so P relative is still the same value. So I'll just note that P relative is unaffected. Okay, it is unaffected by the force. Okay, it only depends on gamma and m. Okay, and then I mean you could say v, but you got v from gamma, so it's sort of there. It's self-referencing. So all you need to know is this. You don't need to know anything about the directions. Okay, so finally part D. All right, so we're gonna have both components of acceleration now. So I'm gonna have my parallel component and my perpendicular component. Okay. Now, one of those is going to be the parallel force. Okay, in this case, we're just going to have cosine and sine of 55 degrees. So we'll just call this one, and it'd be clear, which one is. If it was greater than 45 degrees, imagine the force was, 70 degrees to the to the velocity. Then you could figure out, with a sketch or with your mind's eye, which one is the perpendicular in terms of which one's bigger and which one's smaller. In this case, they're equal sized. So it'll just be f times cosine of 45. Could have just easily used sine, of course. And then we have gamma cubed m. And then over here, we're going to have f sine of 45. And then gamma m. Okay? All right, so that's going to give us the magnitude. What were we asked for? So we're asked for the particles, instantaneous momentum, and direction, and magnitude of acceleration. Okay, so obviously acceleration is our main focus. Okay, so these, in terms of its direction, we could think of these as basically unit vectors. So we could call this, this is in the parallel direction, and then this is in the perpendicular direction. We could also just, if you want to be a little less, obtuse about this, we could just say, oh, well, velocity is in the x direction. So then we could just call this, I hat for x, and then anything that's perpendicular, because we're sticking to 2D in this problem, would be j, all right? So that's just defining velocity as the y direction. So we'll just say that, right? So that's what I called it. Now, perpendicular was j, so we're defining it in the x direction. So it looked like this, all right? So I'm just saying that velocity points in this direction here. Let's get the pin size. Okay. So this will be the direction of velocity, all right? Always just defined as the x direction. So before, we were applying forces either parallel or perpendicular, which meant either x or y, all right? But of course, in this case, we're applying a force at 45 degrees. So this is our force at D, all right? And then that's, of course, be our 45 degrees, all right? Okay, so our perpendicular is, the j hat, nice. Okay, so let's go ahead and just get vector notation on this. We'll just calculate both components. So then go back over here. So as a vector, our acceleration is in x and y components. Well, let's see, right? So at this point, I guess I can just call them ax and ay for this particular one. If I wanted to be really thorough, I might call them a3x and a3y to stick with that, kind of convention. But this is our last one, so I'll just, in this problem, so we'll just keep it simple. All right. So ax, all right, that one is going to be f, okay, times, okay, and by the way, I want to put this all in division, so I'll do that first, okay? And then times cosine of 45, all right? So let's get a function in there, cosine 45. Almost certainly I'll have to change it to degree mode. It's going to be defaulted to radians if I've turned off the app at all. All right, so there we go. Then we just have our g cubed term, gamma cubed, right? Get in the habit of calling it g, and then times m. Okay. Looks good. All right, so that is our x component, which will be our smaller one for sure. Parallel will always be smaller. And then we'll do almost the same thing. So we'll copy it down. The only difference now is we'll change the sign, which won't matter here. But what will matter is when we get rid of that cube down in the numerator. All right, that's going to make a big difference. All right, so we got the sign up top. And then this, of course, we'll get rid of it. All right, so 165. Nice. Okay, so great example of at these high speeds, we can see which acceleration is really going to make a big difference. So this is going to be 16.2 meters per second squared in the I hat direction, which is also the parallel direction, and then plus 167 in the perpendicular direction, meters per second squared, j hat. Okay, so that would be our vector. We'd be done there. We could certainly put a box around it and say that's our vector. If we wanted to find its magnitude, we're just going to use the Pythagorean Theorem. All right, so then its magnitude will just be, I'll do the calculation over here, but I want to finish off this problem. We'll put the last part of part D on the next page, but I'm going to squeeze this in here. So it's just the Pythagorean theorem, so square root, and then we are just going to take ax squared and then axy. All right, I need to relabel this because if I try to use these variables, I will complain that there's two labeled the same thing. All right, so then we got a, and rightfully so. All right, this will be the x1. Okay, and then of course we'll add y. I'll come back and square that in just a second. Okay, so a sub y. All right, and then we will remember to square both of our variables. All right, great, excellent. So it looks like, yeah, worked that out really well. And this one we'll call A3 because it is the magnitude. I suppose that's sticking with the notation, right? Because those are all magnitudes before that I reported. They actually could have been vectors again because they're one-dimensional, but I never gave them directions, so they remained as scalars. All right. So 167 is, so you can see that 16 is, as often is the case with square roots, the much smaller number, it hardly seems to have an effect and doesn't within rounding. So 167 meters per second squared is the magnitude of the acceleration. Now, finally, it asks for the angle between A and F net. So how would you find this? Okay, well, this is a good little application of calculus where we use the dot product to find the angle between two vectors, okay? Actually, we don't have to here because we're two-dimensional. All right, so normally we would use the dot product. So normally, all right, and I guess normally would be for 3 dimensions, for 3D problems. Okay, we use the definition of the dot product to find an angle between two vectors. Definition of the dot product to find the angle between two vectors. Okay, well, but here, do we have to? No, because it's being two-dimensional, we can really just think about triangles, and we don't have to, worry about those triangles being in 3 dimensions and tilted and skewed and all that. So we can just deal with this in a nice, straightforward way. I don't know why I made that axis so much longer than the other. So we'll just call this x and y, and we'll stick with having our velocity on the x-axis. All right, but we will make it a larger pin. That's a little narrow last time. So this will be our velocity. We've already established that the force is being applied 45 degrees to that, but now, thanks to the amazing weirdness of relativity, the acceleration is not parallel to that F net force. Okay, I just keep calling it the force because, kind of simplifying things, but it very much is the net force. Otherwise, this wouldn't work. And so let's think about it. Like looking at our values, right? The y1 is way bigger. It's about 10 times bigger. Like kind of nice, right? So actually, if I was to eyeball this, I just want to make sure I draw a vector that's 10 times longer one way than the other. So I use purple. So maybe something like that, right? So the reason I know that is because if I think about the components, well, this is the perpendicular component, right? And I'm just saying that the perpendicular component is about 10 times longer than this right here, which would be the parallel component. Doesn't want to do it straight there, right? So this one would be the parallel component. Just to label those real fast and actually label everything. This is A, right? This is our instantaneous value of acceleration. That's always what we're finding. And then these are just the 2 components. So a parallel, the small one, and the really big one, right? This one, a perpendicular. Okay. All right. So with that, the angle that we were asked for was the angle between them, which would be this angle right here. All right. We'll call that phi. Put that in a different color, actually. It's too similar to the other one. How about this color here? That'll work okay. All right, so this will be our phi value. All right, so how do we find phi? All right, so looking at it, what's going on? Well, we should just be able to basically subtract the angles, because if we know this angle here, right, then we know that all 3 of those angles add up to 90 degrees. So kind of a beauty of that, right? So we can definitely work it out that way. All right. So I think that is a nice, straightforward way of doing it in terms of actually finding the angle. Is just go ahead and find this angle, which I will call beta, because I've already used theta and phi. And if I wanted to find beta, that should be pretty straightforward. Beta is just equal to, there we go, inverse tangent, all right, of the 2 components of acceleration. We can tell which one's opposite and which one's parallel, obviously by looking at where we define beta. And opposite's parallel, and the other one is perpendicular. So that means that beta, all right, is going to be, we can easily do that over here. All right, we'll call it B, and we'll do our inverse tangent, still in degrees. Okay, and it's just going to be AX over AY, okay? Because remember, X is the parallel one. So A sub X, all right, divided by A sub Y. Okay, looks good. All right, so that's 5.57 degrees, a small angle like we'd expect. I'd probably do it way too big. So 5.57, all right? So then we can say that phi, right, the angle between, is just going to be 90 degrees minus theta minus beta, okay? So that will give us that phi. All right, the angle between F and A is 90 degrees minus 45 degrees minus 5.57 degrees, which I will go ahead and tell us what that is. All right, we'll call this P for phi, and it's going to be 90 minus 45, so I could have just done 45 for that matter, but then minus B. Okay, so 39.4 degrees is the angle between the two vectors of force and acceleration, vectors that classically would always be parallel, but here are definitely not, okay? All right, so that definitely concludes this problem. I think I've been going for a while, so I guess I'll go ahead and leave the next example as a separate video. The only difference with this one is it's three-dimensional, so that's the kind of the upfront difference. And we've got what is the angle that the net force vector makes with the initial velocity of the electron, so that's just me using the dot product. What is the angle that the initial acceleration makes with the initial velocity of the electron? All right, and then what is the angle between the initial force and the initial acceleration vectors? Yeah, so in fact, actually, we can reason out A and B. So basically, we may not actually need to use the full dot product between some of those, depending on, because I see here that there's lots of I hat and J hat components. I don't see a lot of K hat at all, right? Obviously there's going to be an effect because I give you a magnetic field that's pointing in the Y direction. That's gonna produce a force in the Z direction. So essentially, what this one has is there's an upfront Lorentz equation. So we actually Lorentz force equation, that is, not to be confused with Lorentz that we use for relativity, Lorentz factor. This is Lorentz as it applies to classical mechanics. Or in this case, electromagnetism. But regardless, the Lorentz equation is how we deal with the direction of net force when there's both a magnetic field and an electric field pointing in any direction they want, completely three-dimensional. And so it involves a cross product, which is going to give us the result for the dot for the magnetic field, and then it's simply multiplication for the other vectors. Yep. So that's going to be a little bit of difference, but like I said, I'm going to save it for another video. So go ahead and tune back in for part 2 of going over these examples. Okay. All right. Well, hopefully I will see you then, and I hope this video has been interesting and informative. Bye for now.